G'day viewers. In this segment we'll talk about distance vector routing, which is one of the two main approaches to routing. So we've learned about shortest path routes in a network, and we've also seen algorithms such as Dijkstra's algorithm to compute those routes if we have the network topology in front of us. What we're going to talk about now though is a routing algorithm which could run in a real operational network where every node doesn't a priori know the complete topology. We'll look at the distance vector approach. It's called this because every node maintains a vector of distances to other nodes and they exchange these vectors with one another. So distance vector routing is a fairly simple routing algorithm. It's been used for a long time in both the ARPANET, it was used at the beginning in the ARPANET, and also in a protocol called RIP. It's one of the two main approaches to routing. Now it doesn't use Dijkstra's algorithm as part of it. We'll see the other approach that does. If you want a fancy name for it, you're at a cocktail party, you need to tell people what you're studying. You can say it's a distributed implementation of the Bellman-Ford algorithm. But we'll see there's really not so much to it. Basically the algorithm will work and compute the shortest paths for us just fine. But it suffers from very slow convergence for some kinds of failures. Because of these problems, another class of algorithms that we'll see later, linked state algorithms, are more widely used in practice today, and distance vector is rarely used. Linked state algorithms are going to turn out to be more involved but give us better behavior. So to get there, first of all, we're going to learn about this class of algorithms. That'll get us on our way to understanding a style of routing. And before we even get into the algorithm itself, I want to remind you of the setting for routing algorithms. It's different than this setting where we have the whole picture of the topology. If we just had a map of a network and you could run your algorithm on it, routing would be easy. But we have to do this in a distributed decentralized setting. So in particular, if you imagine this running network when it's operating, the nodes only know the cost to their neighbors. You just have your local information. They don't know the complete topology, so they're going to have to deal with that. They can only talk to their neighbors to find out what's going on using different messages. So they can only hear indirectly of information that's further away. All of the nodes in the network are going to run the same algorithm concurrently. So there's no special node that's a controller or in charge who knows any more about the network. We're just going to have to sort that out and have the nodes all agree amongst themselves on the right decision. And as well as this, for just the nature of routing, we would like to be able to adapt when there are failures of the links or the nodes which are running this protocol itself. They might all crash and stop working. Messages might also be lost too. So here's the algorithm, just an outline of the distance vector algorithm, and then we'll see an example. So in the distance vector algorithm, every node maintains this vector of distances to all destinations. And the vector tells us the distance to the destination, and we also remember the next hop for the destination, because that's what we need to know for forwarding. The algorithm works like this. In the beginning, a first step is just to initialize your vector. You know that you're zero cost from yourself, and you can set the cost to infinity for everyone else, and that's good enough to start. Then you periodically send your vector to your neighbors. Now, of course, they're all running the same algorithm, so they're going to send their vector to you. You're exchanging vectors, really. Once you get vectors from all of your neighbors, what you do is you update your vector. You look at all of these vectors, and for every destination, you essentially take the best option. You'll hear of different costs to reach destinations via different neighbors. You can find out what the cost would be for you by adding the cost of the link to your neighbor over which the message passed. So when you compensate for the link costs and pick the best routes for every destination, you'll have a distance to every destination, and you'll also know the best neighbor, and you can use that for forwarding to reach that destination. This is the theory. Let's see how it works in practice. Here's our example network, the same network as before. We're going to consider this network from the point of view of A. So we want to know what is going to happen at A, so we can compute routes to reach everywhere else in the network. Now, of course, A can only talk to the nodes B and E, and I've shown the links that it uses in black. Everything else, we can see it, but A doesn't know that's out there yet. It doesn't really exist as far as A is concerned. Okay, so A's initial vector is this. It's shown here. You can see it has cost 0 to itself and cost infinity to everywhere else. Let's see what happens. Here's the first exchange. Now A is going to send its vector to B and E. Well, they're going to do the same thing. They have an initial vector and they're going to send it to all of their neighbors including A. So we can see from B we will get this column here. For all of the different destinations, B knows it can reach itself at cost 0. It doesn't know how to get anywhere else yet. E similarly. E can reach E at cost 0. It doesn't know anything else. We've all just woken up. Let's adjust these costs so we could reach B. Well, the vector from B came over a link with cost 4. So this really means that A could reach B over the link AB at cost 4. We add the 4 to everything here. And similarly, A can reach E over a link with cost 10, so we add 10 to everything in E's vector, and we get these two vectors. Here's the one for B, here's the one for E. Okay, and that's our input vectors from all of our neighbors. We look across these vectors for each destination and pick the lowest option we have. Well, for ourselves, reaching A, that's a bit of a special case. We're already there, so we're at cost 0 from it. We're not going to change that no matter what we hear from other nodes. We've learned, however, that we can reach B at cost 4 over the direct link and E at cost 4 over the direct link. I've shown these entries in pink just to show you that they've changed. They're better routes that we've learned. Everyone else, we still don't know how to reach C and D and F, G and H. Okay, next iteration. Well, in this second exchange, we're actually going to end up learning all of the best 2-hop routes. If you were observant, you might have noticed that in the last round, A learned all the 1-hop routes from it, really how to reach B and E. Now we'll learn all of the 2-hop routes. B and E are going to send their vectors to A. The tricky bit for us is actually to work out what's in these vectors. If you ran the algorithm yourself and you emulated it from the point of B or E, you'd know what's in their vectors. I think you're just going to have to take my word at it and work through the network. I can tell you that B will essentially know the costs to all of its 1-hop neighbors in the same way that A did, and it will be telling A that. So B can actually reach A at cost 4, B it's already there, C at cost 2 in the graph, you can see. A is not connected to D, A is connected to E at cost 4, F at cost 3, G at cost 3, and not at H. And similarly, E is going to send all of its 1-hop or immediate neighbors. Now I've adjusted all of those vectors. For the B vector, I've added 4 to everything to get this column here. For instance, the 4 there goes to 8, the 0 goes to 4, the 2 goes to 6, and so forth. E, I'm going to adjust that vector by adding 10. And that's, of course, because the link from A to E costs 10 units to go over. That gives me this vector. From this vector, the distance vector rule is just I select the minimum, the best option, essentially the minimum distance to reach each destination. A is a special case because we're already there. B we already knew actually. C, 6. D, now we actually know that we could reach D at cost 12 via E. That's interesting. So we have this route from A to D right here. Now we're going to find out we're going to find a better route eventually, but right now this is the best route we know. We have seen that to reach E, interestingly, this changed. You might have noticed this has fallen. Previously we could reach E directly at cost 10. Now we found a better route to E via B at cost 8, and that is this route right here. So things are getting better with our distance vector. We've learned the best 2-hop routes. And again, everything in pink is new. It's an update. Okay, let's proceed with this, and we have to do another iteration. This looks like a lot of work, but remember that all of these nodes are going through this algorithm in parallel, and all of the steps are really fairly straightforward and easy. You're just sending a message, remembering things, doing simple addition, and comparisons to pick the best option. The third exchange. Now we're going to end up learning the best 3-hop routes that are in the network. B and E's vectors are going to contain the best 2-hop routes. these nodes know respectively to tell A. So B sends its vector, which is here. You're just going to have to trust me or work this out on your own, but it is all of the best 2-hop routes from B to reach all other nodes. For instance, we have in there H is now reachable at cost 5. That used to be infinity, I think, but B has found out how to reach H at cost 5 as the information is propagated. Similarly, E has all of its best 2-hop routes. We'll go through the same steps of adding 4 to B to get this column, adding 10 to E to get this column, then selecting all of the minimums across these rows. What happens? Well, you can see several of these ones didn't change, but we did get better options for a few ones here, where we already had routes, I think. H is new. We didn't know how to get to H before, but now we had a route to H here. However, to get to D and E, the costs has now gone down to 7 and 8, and we go via B. That's because we found these routes. To get to E, it would be this shortest. This is the best 3-hop shortest path. And to get to D, it is this is reachable at cost 8. So you can see that we're finding these new paths. These are paths of distance 3 that we know about now because information is propagated that were better than the previously best paths of length 2. Okay, and finally here's another iteration, and you find actually that everything is converged. B and E are going to send slightly different information here. They now know their best 3-hop routes. They're going to send that to A. Again, I've gone through and added the 4, and you can work through this table by yourself. And you find if I take all of the minimums, I will get all of the entries I had before, so nothing's changed. Now in this table, the costs are kind of interesting because we know how far away all of the different nodes are in the network. The next hops are not very interesting just in this case because A essentially sends everywhere via B. If I'd chosen another node though, E for instance, E would have used different next hops depending on what destination it was trying to reach. And this is distance vector. It's it'll make your head spin after a little while, but the individual steps are fairly straightforward. And conceptually, you should think of information propagating and taking the best options over time. Okay, so I'd like to tell you just a little bit about the dynamics of distance vector. We looked at the case where you just boot up the network and everything's fixed. That's great, but the whole point of a routing protocol is to adapt to failures. Well, let's imagine some changes. One change would be to add new routes, a new node or new links. Well, in this case, we'll end up hearing about new destinations, or the costs to existing destinations are going to be lower because the new links provide better options. This will be new news, and this news will propagate at 1 hop per exchange. What about if I remove nodes? Well, when a node fails, it can't send you a message saying, "Hello, I just died, would you please compensate?" because it's no longer there. However, since it's no longer there, it will no longer be sending the exchanges. Other nodes won't get its information. Eventually, if they can forget or discard that information, and we will have removed their information from the network, and we will end up finding the best routes that remain when they're no longer there. However, for distance vector algorithms, there's one case which is very difficult, and that is a partition. That's when there are unreachable nodes in the network because there have been failures that divide the network into more than one piece, into multiple pieces. These are a problem, and they can lead to what's called the count to infinity scenario. Let me show you that scenario. So here it is. On the left side, this is the situation where everything is fine. This is just a very simple topology to illustrate it, a line, A, B, C, D, E. Pretty straightforward topology, this chain. It's a chain topology. And after the exchanges, you can see that the costs settle down. So to reach A, B is at cost 1, distance 1, C distance 2, D distance 3, and E distance 4. That's where we've settled and we're all fine. Now let's suppose we're there and there is a failure. This link goes. This was the only link with which we could reach A. So A is nowhere to be found now. What's going to happen? Well, A will not send its information to B. B will hear that C can reach A at distance 2, and that's the only option it will have to reach A. So B will say, oh, okay, well, I can reach A at cost 3 or distance 3 via C. Well, that's a bit of an unfortunate choice because, of course, it will then advertise that to C, and C will say, well, wait a minute, I can't reach A at cost 2, I can now reach A at cost 4. If C can reach A at cost 4, guess what is going to happen? The next time around, B will reach A at cost 5, and D will reach A at cost 5, because C's cost has gone up and D was depending on C. Well, this is terrible. What else is going to happen? Well, that information will keep going around. You can see that C's cost will go up, because really, you could almost draw the arrows in to show how this information is propagating. And so forth. And as you can see, this pattern is going to continue and will keep inflating things as the information is shifted around the network. This is called a count to infinity scenario because it's going to keep going as the costs get higher and higher. Essentially what happens here is that while good news travels quickly and directly because you're basically telling someone the good news, this bad news travels very slowly because it has to be inferred by exploring the whole network to see if there is a possible better route to reach A. The way we explore it, we're counting up all of the different costs and exploring routes further and further away, just in case there's something good out there. Eventually these numbers will hit the constant called infinity, and we'll decide that something fishy is going on here and this node is no longer reachable. But as you can imagine, this is a very nasty scenario to get in, because while this is going on, messages to A are simply being looped in the network and they're occupying many network resources. Now there are various heuristics that can be used to address this problem. You might have thought that it sounded a little contrived, that C would tell B how to get to A, when really, of course, B told C the news in the first place, and B will be fooled into using that information. That does sound weak. There are heuristics that can be used to avoid that. They have colourful names. One of the most popular ones is called split horizon with poison reverse. All of that really means is that split horizon is just you don't accept back from nodes information you already gave them, so B won't be fooled. Poison reverse is just when you're telling someone something that they learn, that you learn from them, you can even give it a bad cost, just to try and make it unattractive. But these heuristics don't really work. While they deal with this problem we saw, you can have cycles over a larger number of nodes where the information is spreading along different paths that can be difficult to detect. So since none of these heuristics turn out to be very effective, this is a major reason why link state protocols are more favored in practice. These link state protocols, we'll see them in a while, they turn out to involve more computation. They run Dijkstra's algorithm, for instance. This is generally fine, but it is more computation intensive, and so when the situation is very resource constrained, we might prefer a distance vector algorithm. Finally, let me just briefly mention RIP, the Routing Information Protocol. This was a very popular and widely used routing protocol based on the distance vector algorithm. It's not widely used anymore. It was widely used if you go back a couple of decades. You'll still see it around today in the internet. Nothing truly dies. It's a distance vector protocol, a particular implementation of it that's used in the internet. It has hop count as the metric, so the cost of every link is 1, and it's just trying to choose the smallest number of hops to get from one destination to another. The value of infinity in this network is 16. Okay, so this is going to limit it to small networks. That's all it's really intended for. And it includes these heuristics with the colorful names, split horizon and poison reverse. Now in RIP, routers send vectors every 30 seconds, so that's our periodic announcement. These vectors are sent over UDP, so they're an application in some sense that runs on top of UDP. There's a timeout of 180 seconds for failures, so if a node does not hear information repeated from another node within 180 seconds, it says that node's dead and gone. and it can safely remove all of the information that was coming from that node. The multiple 180 seconds, you might have noticed that's almost 6 messages. This is to allow for a little bit of unreliability. Since the messages are sent on top of UDP, you could lose the odd routing announcement, or maybe it could be delayed for some reason. So the longer timeout is just to allow for some message loss before declaring a major failure. Now, RIP, the initial version of RIP version 1, is, you can see it dates from 1988. It's specified in one of these RFCs, RFC 1058. There are many RFCs that relate to our protocols. I'm not going to point out too many of them. I think you can read more about them in your book if you would like. But I'll point this one out just because if you're interested in seeing a specification of a protocol, this is one that's fairly easy to read. Generally, all of the earlier ones are easier to read because nowadays protocol specifications can be very, very long, hundreds of pages. But these earlier ones, we're just talking a dozen pages or so most likely. I forget exactly how long. But it's quite readable is my recollection. Okay, so now you know about distance vector routing.